during COVID, we've all had to do various things. And one of the things I picked up is hypnosis. And I learned that Alan is deeply hypnotizable. And so what I've been doing the last few months is I'll just hypnotize Alan and pull him back, forgetting the last 20 years or so. Oh, crap, I need my slides. Sorry about that. Because there we are. So I'll take him back about 20 years and just pose him the same problem. So it's I ask him to give me a model of imperative programming that supports shared memory concurrency and it's compositional, for parallel composition and sequential composition, and a few other things. Anyway, he always gives me a different answer, and so we'll see what happens this time. I'll just wake him up. Alan.
Hello. Hey, James.
Hey, Alan. So I have a question for you.
Oh, sure.
What's an explanation of this program here? It's a program with sequential composition. How would you explain it?
Oh, all right. Well, that's stuff from 20 years ago. It's like from the 70s. It's like, we just do preconditions on that. And
that's true. So what happens here? Walk me through it.
Yeah, all right. So, we could do it using core triples. So you start out with the post condition. So we're wanting to know that y is 1. And then from that, we calculate the precondition. And then we feed that back into the next thing, right? So and keep on going. So you chain those preconditions through each other until you get to a precondition true.
Okay, that's quite beautiful. And this is actually similar to the theory of predicate transformers as well, isn't it?
Yeah. So this is all this is known stuff. This is like 20 or 30 years old.
Okay, great. That's awesome. But what do you do with concurrency?
Oh, all right. I guess that's slightly harder. But there's been some fairly recent work, hasn't there, on like shared memory concurrency models. So we can put in order defense. So we can, let's take this concurrent program, right? We build it for the read and write events for that thing. And then we chain them together for the ones that are ordered. So within a thread, there's order. And between threads, well, there is some order because you want, reads to happen after the writes. And you probably want to know that anything that's a blocker, like that write, blocks the write of X. So you want those to be ordered as well. So you put in blockers, but otherwise it's mainly just thread order.
Okay, that's great. But what about hardware? Hardware can reorder these things, Alan.
Oh, can it?
Yeah.
That's right.
Look.
Multi-core systems have just come out.
Yeah. Anyway, look at this thing. So this is a program. It's writing X and then reading Y in one thread, then writing Y and then reading X in the other thread. And then by your analysis here, in order to justify those reads, I have to put in order here, which gives me a cycle. So therefore, this is no longer a partial order, and I'm in trouble. What do you do?
Oh, yeah, all right. I guess there is that all this weird stuff about caches that will cause this kind of thing. Okay, we're going to need to deorder. So yeah, it just that requirement that the threads produce order. I think we're going to have to drop that.
Okay, that sounds great. But what about SCTRF?
What? What's that?
What about thin air?
What?
What?
What are the? I do not understand your words.
You can't just drop that order. Look at what happens here. So here I have a thread that reads X, and then if it sees a certain value, writes Y, and then the other thread does something symmetrical. If I drop that order, this execution would be allowed, and yet this is clearly a nonsense execution.
Oh, all right. I see what you mean by that. Okay, so we need some kind of notion of dependency, don't we? So in this case, it's a control dependency.
Yeah, that's great. So wait, how are you going to do that exactly?
Well, okay. The obvious thing to do is to read off dependencies from syntax. Just use the 3 variables.
Okay, that's great. All right, so that's going to solve this particular problem, right? Because that control dependency will now be in introducing order here, and therefore forbidding it, right? But what about compilers?
Yeah, all right, that's right. Yeah, compilers still do all of their optimizations assuming single threadedness, don't they?
Yeah.
Okay, yeah. So like that example there, the semantics of that assignment to y is going to be constant 0. So we need to like use semantic dependencies as a way of calculating dependencies, not just syntax.
Okay, fine. All right. So you've got this idea, semantic dependencies. That's awesome. That solves this problem. But it's a great idea. How are you gonna do it?
All right. Well, going back, we had this notion of preconditions and predicate transformers. So maybe what we could do is we could take these POM set models and then we could put a precondition onto each event. And then like calculate a predicate transformer that will tell you how each program like changes the preconditions.
Wait, how is that going to work? Wait, I don't understand.
All right. Well, okay. So let's take an example program here. So the precondition of being able to write 1 into x is the s equals 1. And we read 1 into s from that read action. And so now what we want to do is we want to compose those two together.
Okay.
So we want a predicate transformer over on the left. But the thing is that in order to get this notion of dependency and independency, we need to keep track of which set of actions it is, what set of events the transformer is going to provide. So, like in this case, okay, if you depend on that read action, then you get to assume that s equals 1. Whereas if you don't, so you're the empty set of events, then it's just the identity.
I see. And so with this introduction here of this weakening of the precondition, so now all those preconditions are tautologies. So all we have to do is require that they're tautologies at top level.
So by the time you get up to top level, everything's a tautology, and so all the events can fire. So that's the case of dependency.
So for independency, what happens?
Yeah. So for independency, rather than taking the case where you actually did depend on the event, you take the empty set case because you're not depending on anything. And that means you're using the identity predicate transformer. So you still end up, when you do the composition, with that, that horrible arithmetic expression on writing y is 1. But that's a tautology. So now everything here is a tautology. So that's a valid top level POM set.
Wow. Okay. So tautologies, we can just erase them, and it looks like we wanted.
Yeah.
Yay!
Yay!
Yay! That's pretty good. But yeah. So I mean, what's really beautiful about that idea is this idea that in the logic, you've got this idea of capturing local order, and then the POM set is capturing the order of the local events, this thread's events that are seen by other threads. So it's kind of this global order, the other order. That's really beautiful. But what do you do with control independencies?
Oh, okay. What would an example of a control independency
So something like this. So here we're reading x, and then based on the value, we either do one thing or the other. But you can see here that actually those dependencies, the conditionals there are false dependencies, right? Because we're going to write 1 regardless.
Yeah, okay. I can certainly imagine a smart compiler would be able to work that out, that in fact that conditional is unnecessary, and it will just like rewrite everything to y is 1. So there'll only be one y event. All right, okay. So what we can do is we can merge them. We can do the same thing that the compiler does syntactically. We can do it semantically and allow you to merge together events.
That sounds about right. And then the precondition then is the disjunction.
Yeah, it'll be the disjunction of the two preconditions.
Very, very, very nice. Okay, that's a wonderful semantics. But is it, does it have the properties we want? Is it, for example, just to pick one, is it associative?
Oh, good question. I guess like that is a basic thing that you want out of sequential composition. If you're going to like give a semantics for something called semicolon, you'd at least like it to be associative.
It's pretty basic, yeah.
But it should be. I mean, like my gut feel is that it is. It's like
gut feel.
It's based on composing.
Your gut feel. Oh my God! If I had a dime for every moment. In any case.
All right. Okay. Well, let's go through an example. Right. Okay. So here is like 3 of those POM sets. And now, we've got 2 ways of stitching them together. So if we do the left,
let's go with the left.
Yeah, do the left-hand side first. Right. Well, in that case, we want those 2 events to be independent. So we take the empty set case, And now we compose together the predicate transformer, and then we apply it to the right. Okay, and we get a dependency on the rewild action. Yay, right, okay, and that all worked. Right, now if we associate to the right, we do the same thing. And we take the dependent case, do the predicate transformer, and then compose again with the thing on the left. And we take the independent case, yay, all right. So at least in this case, it worked there. Nothing could possibly go wrong. Yay! All right. So I think that seems like about kind of like a modern 1999 kind of POPL paper. We've got a model. We've proved some properties about it. Right. Okay. We submit.
Yeah. Yeah. The sad thing is, it's not that way anymore. Yeah. You got to have formalized proofs. I just don't know what. Oh, wait. There's this gentleman in the audience.
Oh, all right. Hang on a moment.
I've typed in some proofs for you guys.
Really?
Yeah.
Really? That's so nice. Wait, what do they look like? Oh, is that it? Wow, that's really short. That's great. I love that.
Well, there are 13,000 more lines of them, to be fair.
13,000 lines? Well, how do we know that any of that gobbledygook makes any sense?
Well, the proofs are in Coq, so they are all verified.
Woohoo! All right, well, that's fantastic. But, you'd think we were done.
Yeah. That's it. Okay. Right. So now we've got a model. We've proved some pen and paper results about it. We've then taken those pen and paper results, mechanized them in one of these, 12th style theorem provers that I've heard about. We're done. Right. Yay. Submit. Hurrah.
Yeah. No, sadly, it's not enough. So we actually have to show that this stuff works on some sort of real hardware. And, at least here, I have an idea. So I think that taking this idea of your beautiful model, which is that the logic is somehow capturing this thread local order, and the POM set is capturing the order seen of the thread's events by all of the other threads. Now, all those other threads, if they all agree on that order, that's what we call multi-copy atomicity.
Oh, I'll take your word for that.
Okay, so anyway, so this is quite nice. So we can actually just add a little bit to your semantics to include things like coherence and, sort of non-relaxed access and fences and things like that. And if we include that in there, we actually get a really natural model, which is optimal for ARM8. Yeah, just trust me. And so it's optimal for this processor. On relaxed access and released access, it's not going to be optimal, sadly, for acquiring access. You can look at the paper for that. But with a little bit of work, we can actually come up with a model that's optimal for all three forms of access. So there you go. This actually is a really nice result. It corresponds to two alternative formalizations, which are going to be presented on Friday in the top list section. And it's great, except that we haven't handled all the other architectures.
There are other architectures?
Yes, sadly. Oh, actually, you know about Power?
Oh, that's right. Yes, I've heard about these.
Yeah,
these
Power is not MCA.
All right. Okay.
Yeah. At that point, I think we're stuffed. Unless somebody speaks up.
Simon?
You considered making this work for C instead? That can target non-MCA platforms.
For C?
Yeah, the programming language.
Wow. Okay, so wait, how would that work?
Well, I mean, you've got these dependencies. If you replace this axiom that SB union RF is acyclic with dependency union RF is acyclic, you'll have a pretty nice model.
Yeah, that's interesting. Okay. Yeah, that's actually been speculated for a while. So in fact, you've done some work on that.
Yeah.
So SB is like synchronized before. That's program order in C speak, right? Oh, okay. So that's nice. Except, the thing I can see, a problem here is that SB is actually used all over the axioms for C11. It's not just there. And SB is like, it's an actually essential part of the model, right? So, and in our model, the natural form of SB, it's gonna give you cycles. So look here, if you merge, right? So you merge the left and the right here, we're gonna end up with cycles in synchronized before.
Well, maybe you can just keep track of this as you're doing it, and you can undo it with phantom events.
Oh, okay. So we've got some phantom events keeping track of the real events. And then I guess what's going to happen here is that at top level, only one of those two sets of phantom events would be there, and then we can sort of eke out what would be program order for a given execution.
Yeah,
Is that the idea?
that seems fine. Yeah.
Oh, that's great. Okay. And can you do tooling for that?
Oh, well, I've built a tool.
You built a tool?
Yeah.
Just in the time of the talk. Wow, that's impressive.
Very fast.
So let's see what it looks like. Oh, that doesn't look good.
Oh,
So that's it?
well, no. I've also run a bunch of Java causality tests to it and verified the result of common litmus tests.
Okay, but I see some unpleasant looking symbols in there.
There's a small problem with the state space for the predicate transformers being exponential. So it times out on big tests with, some number of instructions.
I see. But we do have some tooling though.
Yeah.
That's good. I don't know. Do you think this is good enough?
I think we could declare victory at this point.
Let's be done with it.
Yay.
Yeah. All right. All right. So what have we done, Alan?
All right. So what we've got is a model, a denotational model of sequential composition, and this is for a concurrent shared memory language that's been run through all kinds of weird optimizations. And the idea that we're doing in this paper is that we're calculating dependencies because those go into POM set order, and POM set order is what other threads get to see. So there's a distinction between the local, for each thread, it's a local notion of order that is given by the obvious thing of sequential composition, and then the order that the outside world sees, which is just dependencies. And for MCA architectures, like this is really nice. So there's a really pretty little model for which gives you nice Tixie diagrams for MCA architectures. And so that gives us a solution for the out of thin air models, so like C and JavaScript. I've got problems with the UTA behavior. And it's a denotational semantics, which means that we can actually do like a tractable presentation of POPL optimizations. It's just like, right, very obviously you read off the sets of events, and it's just subset order on sets of POM sets. And these are actually understandable diagrams. I mean, this bit is hand waving, but I find these diagrams a lot more easy to understand than other models that might exist.
There are weasel words there, but if you've been in the literature, the weasel words are not unreasonable. Maybe, pick your weasel words.
Right. Okay.
In fact, there is some complexity.
Yeah. I mean, so there is some downside. So you do have to calculate these dependencies.
Yeah, and that's got that exponential blow up.
And there's this weird thing that hardware models assume that you've got atomic events for load and store, but compilers do not believe that. They are very, very happy to take what looks syntactically like a single assignment or a single read and turn it into like who knows how many reads and writes. And really weirdly, as you can see from some of the examples here, like when you're doing the semantics of conditional, normally when you're doing a denotational semantics, an execution of the conditional depends only on an execution of the branch taken. Whereas here, we do actually depend on both branches. So we take an execution from both sides because we might need to merge some events from the two sides.
Yeah, in fairness, there doesn't seem any way around that. So there's a lot more in the paper, I suppose. But to me, the big takeaway for this is that concurrency is actually not that hard. I mean, in fact, the first thing that you came up with for POM sets, it's still the thing we're doing for concurrency, right? So, but for sequentiality, that's actually a hard problem. So because here what we're deciding is the order that's seen by other threads. So it creates this difficulty. And so thank you for your attention.
That was fabulous. So we're going to start the next talk at 2, just because we're running over. Let's start taking questions from the room. Oh, and I guess I'll run you the mic.
We'll see.
I assume there are at most 5 or 6 more lines of code in this 12-like prover to connect that to your tool?
I'm not sure what the question is, actually. Oh, and the tool. Yeah. Actually, do you want to take it? So what's the connection between it's a litmus tester, right? That tool and the one here. It is an informal connection. So we've had to elaborate the semantics. Do you want to take it?
Yeah, so the tool is implemented in OCaml. You know, we sat down and thought very hard writing OCaml with the mathematics in front of us. It's not formally verified like the cock is. There's not a great way around this. The tool is complicated and may have bugs because I'm a human, but it does what we expect for the litmus tests that we've run by hand on the whiteboard at great pain and, you know, mechanically. So we've got some faith in it. It's not much faith.
So we're going to take one question from online and then one more question, and then I can in theory, the online question is not up to you.
Okay. Ta-da! Ta-da! Online question. We can read it.
How suited is this model for reasoning about program executions, i.e. program verification or program logics?
Right. Okay. So see our previous OOPSLA paper, I think. We didn't talk about it here because this is actually from the paper that this builds on. But in the previous paper, there's a temporal logic that, like, the first very simple temporal logic that we could think of. So it's not a separation logic. It doesn't do anything clever, but it is good enough to, like, verify some of the UTA examples that we ran it through.
That's out of thin air examples. Yes.
Oh, sorry. Well, I've now flashed forward in time. We do have a program logic, but it is a really simple logic. Yeah. And, you know, the obvious thing to do to it then is to take it and plug it into a separation logic. But that is left for future work.
Yeah.